to our game, Do or Die. What we are trying to get today is to find the biggest number out of each roll. Our goal is to get the highest possible number. What you want to know is if you should stay on the first roll or roll again. You need to find your expected value for each roll and what number you should stay on if you have 3 rolls. Also, if you roll the die 1,000 times and can only stay if you have a 6, what would be the smallest number of allowed rolls? The expected value of a random variable gives a measure at the center of the distribution of the variable. Essentially, it is the lay term average at the variable. So for our first roll, we expect our chances of rolling a 4, 5, or 6 to be the same as rolling a 1, 2, or 3. The expected value of rolling any one number would be 3.5, or an equal 1/6 of a chance. If your first roll is above 3.5, 4, 5, or 6, keep it. If it's under 3.5, roll again. And our equation would be 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3, and so on until you get to a 6, which is 6 sides of a dice. For your second roll, your expected value is increased as half of the first value's roll will be below 3.5 and half will be above. This will change the equation to 0.5 times the 4 plus 5 plus 6 divided by 3 plus 0.5 times 3.5, the original expected value, which will give you your new expected value for the second roll. For roll 3, you will only keep your die if it rolls above a 4. You will roll again if it is a 1, 2, 3, or 4. This again changes the expected value, as your first set will only contain a mean of 5 and 6, which is 5.5. The chances of rolling that becomes less than 1/3. Our equation then would be 1/3 times 5.5 plus 2/3 times 4.25, which we can look at the board to see Nan showing the tree method as one of the ways to show the work. And then Selena will show the column method.
Okay, for the tree method, we have 6 rolls of a die. These numbers are 1 through 6. There are 6 numbers on each dice. The average of these numbers is 3.5 on roll 1. On roll 2, we need above a 3.5 on roll 2. The average of 1, 2, and 3 is still 3.5, and the average of 4, 5, and 6 is now 5. When we average these two numbers, we get 4.25. On roll 3, we need above a 4.25. Now, the number above a 4.25 is only 5 and 6. So 66%, or 2/3 of our numbers, are average of 4.25, and our 2 numbers that are above are 4, their average is 5.5. We average these numbers together with the 2/3 and the 1/3, we get 4.66. On the fourth roll, we need above a 4.66 average. And in order to get our next average, we take 66% of this is 4.66. 33% of these two numbers is 5.5. So now our new average is 5.12. We need above a 4.94 average on roll 5. When we average the numbers again, we get a 5.12. And on roll 6, we need above a 5.2 average. And we get a 5.26 average.
tree method that Nan just explained, and we have the column method. Here we have our first roll, which gives us an average of 3.5. When we do our second roll, we get an average of 4.25. When we do our third roll, we get an average of 4.66. And our fourth roll, we get an average of 4.94. And our fifth average, we get a 5.12. Fifth roll, we get a 5.12 average. And in our sixth roll, we get a 5.26 average. If you look at all of both of our methods, you'll see that our averages match down here. And the only difference is the setup.
As you can see, the tree graph and the column method shows us how our expected values go up by each roll. At roll 4, it becomes 4.94, and at roll 5, our expected value becomes 5.12. This is where we would have to roll higher than our 5 to overtake our expected value. So we know only to stay if we roll a 6. This tells us our minimum roll is our fifth roll, where our expected value is 5.12, and only a 6 will work.